Okay, now I've done a sloppy job of correcting this thing, but this will at least show you where the number comes in. As we discussed before, and let's just look at the situation. Remember that the table tells us the area under the z-curve, under the normal distribution, between 0 and the value z, and that we're looking at a case where we have a mean of 85 and a standard deviation of 3.4 test scores, and we want to know how many out of 200 in a large class would be expected to score at least 90. And we see that the z-score is obtained in the manner that we usually do. And from the table then, if we look at z equals 1.5, we see that we have 0.433. So that the area between 0 and z equals 1.5 is 0.433 of the total area. So there's 0.433 between the mean and 1.5 the mean of 85 and z equals 1.5, which is a score of 90. We observed that 0.433 or 43.3% plus the 50% on the other side of the mean will lie below 90, below z equals 1.5. The remaining number, if we want to find who makes better than 90, well, we've got 0.423 of the distribution right here. Hopefully you can read that. It's 0.433. Okay, 0.433 of the distribution would lie here. 0.5 of the distribution lies here, so that leaves 0.5 minus 0.433, or 0.067 of the distribution, lying in this region to the right of the 0.433 of z equals 1.5. So that above z equals 1.5 we have this 6.7% of our distribution. So we write that in words. The remaining 0.5 minus 0.433, or 0.067 of the distribution, lies above z equals 1.5. Our conclusion is that the 0.067 of our 200, or 6.7% of 200, or 13 of our individuals score at least 90.